In the last segment, we were talking about sound intensity. We saw what's the meaning of sound energy content. If we stand in the, if you remember, in the tube with a piston oscillating at one end and the other end being at infinity, sound waves were propagating inside the tube, and if you stand at a particular location x, then energy will be propagated through that cross section, and then we calculated that and we call that intensity, sound intensity, and we said that that intensity I is the P plus square over 2 rho C. Okay. And so that is the pressure amplitude which exists at it, the sinusoids. We were oscillating that piston with a sinusoidal motion, and because of which a sinusoidal pressure wave was propagating, and the amplitude of that pressure was P plus. And because we know that for such cases, another way to write that is, P RMS square over rho C. So, because P RMS is nothing but P plus over root 2. So, that is another way to write it. We will come to this, that is why I have written in this form. Okay. So this much we had said, and we also, in fact, first we derived that the average, the time averaged energy at a particular location was P plus squared over 2 rho C squared, and then that is how we multiplied C for this plane wave condition, and then we got this equation or the relationship. Yeah. But the thing is, though we perceive intensity as the sound, but it's very difficult to measure it, because if you remember, we said that intensity is the product of two things, the pressure and the velocity, and pressure is a scalar quantity, velocity is a vector quantity. So you have to, if you want to experimentally measure this thing, it's really very difficult to do that, and that's why mostly we measure the pressure. When you use a microphone to take the reading, basically what you are measuring is the pressure, okay, pressure over the atmospheric pressure, the fluctuation. Now, if we are measuring pressure, so is it not good to write the expression not in terms of intensity, but in terms of pressure? That means I was saying that the sound intensity level we defined, if you remember, as 10 log to base 10 of I with reference to I ref. So this I was talking about, instead of writing in terms of intensity and I ref, we said 10 raised to minus 12, or you can say that in fact this will be 10 log to base 10 10 raised to 12 and your intensity, whatever intensity you have, or you can in fact simply you can write 120 plus log 10 to base 10 of whatever intensity you have in watts per meter square. So that's how you can do, and because you see there is just a factor of C between the power and the intensity, okay, so the energy and the intensity you can say. Mostly the intensity level, instead of that, the sound power level, that is denoted as SWL, is used, and that also is exactly with the same expression, because they are just for the plane wave condition, there is just a multiplication factor. So when you take the ratio, it doesn't matter. So log 2 base 10 of time averaged power to time to the reference power. Okay, so it's exactly the same. So whether sound power level or sound intensity level, whatever is mentioned, so they are the same for this condition. Now, but as I was saying, the measurement of this quantity is always difficult. So can we do something, because we know this relationship, so can we write things in terms of pressure and not in terms of power and intensity? So then it's clearly visible from this equation that if we write I in terms of RMS, just we can write, okay, I'll go to the page. So that will be called, say, sound pressure level, okay, because we are writing in terms of pressure ratios. Okay, so that will become, say, 10 log to base 10, and I, instead of intensity, now I am just writing P RMS squared to P reference RMS squared. Okay, so that you can also write as a 20 log to base 10 of P RMS to P reference RMS. So that is a much better or easier thing to, in fact, measure, because this PRMS, the thing which can be easily measured with a microphone, and using this relationship, because you remember 10 raised to, okay, what I was talking about, I was talking about this P reference, okay, RMS. Now how much is that? That its square over rho c is basically that 10 raised to minus 12 watts, which we were using as a reference. Okay, now this number for air is approximately around 400. So from that, if you calculate the P reference RMS, that will come out to be 20 into 10 raised to minus 6 Pascal. So 20 micropascal was the pressure, the reference pressure which we were talking about, and it's the RMS value of the pressure. Okay, it's not the pressure amplitude, but it's the RMS value. That means the pressure amplitude over root 2. Okay, now with that pressure, if you calculate the ratio of any pressure RMS and do this, take the log to base 10, multiply with 20, you will get the sound pressure level. And that is mostly, if you see the condition of noise or sound at a particular location, this is the thing which will be mentioned, the sound pressure level in decibels. So this is again in dB. Okay, so this factor of 10 here is actually taking you to the decibel thing. Okay, now if these are the definitions, can we say anything about how the relative values are, values of pressures, the P RMS are in normal conditions, and what are the normal decibel values in present the day-to-day situations? So for that, I'll just show you a chart here. Yeah. So see this. So this is talking about some values of SPL, the sound pressure level. Okay, I'll come to this dBA. There is something here mentioned, dBA. I'll discuss it now. What is dBA? But now you can think that these are dBs also. Then it says that in the library or isolated broadcast study, all those kind of places, the decibel level of sound pressure is around 30 dB, okay, 30 to 35 dB. And then if you come to a busy office, normally when people are talking to each other, machines are running like printer machines, laptops, desktops, the fans are running. In such a condition, it's 60 dB sound. And if you see here on the sidewalk, by passing typical automobiles, when automobiles are passing by and you are standing on the side of the road, it's around 70 dB. And when a bus is passing, it's around 75 dB. And then so these are in dBA. I'll come to first the difference between dB and dBA. And if you are around 3 miles from the takeoff of an airplane, jet plane, so then it's around 85 to 90 dB. And then on the platform, if you are standing on the platform, when a train is passing, it's around 100 dB. And then in a rock concert, okay, if you are in a very loud rock concert, if you are there, so it's around 110 dB. And then it's almost on the verge of causing pain in your ears, okay, so that's the level. And at 120 dB, so that's called the threshold of pain, where you will actually feel the pain, okay, after this. So that's how the common dB levels are, I think. Yeah, okay. So and you can always convert these dB levels to their respective pressure levels by obviously this relationship which we just now wrote. That means, yeah, so if you take this to be 20 micropascals, so you can always calculate that. If this is a 60 dB, so let's say what, so 60 dB means what, 20 log 2 base 10, so P RMS by P ref, okay. Now that means it's around 3, so you can, from here you can calculate that, so P RMS is nothing but, you know, or this by P ref is nothing but 10 raised to 3, right? So from there you can calculate that this is nothing but into P ref, so around 20 millipascals will be the P RMS if you are talking about a 60 dB sound. So like that you can calculate the various pressure levels at different dB levels, okay. So, and then one more important thing which I would like to point out is that let's see here, we even when we are talking about pressure, we are talking about the energy content, right? Because so from intensity only we have gone to pressure square, that is how this 20 has come up. So that means essentially we are talking about the energy. Now energy is when they spread in space, they spread in a spherical manner, and its area changes, you know, as r square, 4 pi r square is the surface area of the sphere. So the same amount of energy, once it has got radiated from a source, it gets spread across larger and larger areas which are varying as r square. So that means if we are comparing, say, sound intensity level at 1 minus sound, and then I'll say suppose this one is at R and sound intensity level say at 2R, okay, so this is the point 2. Then what you will get is you know, so 20, sorry not 20, it's 10, so 10 log 2 base 10 of say R square over 2R squared, okay. And then that's how you will get around 6 dB, negative 6 dB, isn't it? So negative 6 dB. Is that fine? In fact, I think here, because the intensity is energy per R square, so I think that I should make like this. So here I can erase this, and here I can write a 2. Sorry. So basically, if this is the location at 2R, that means so here sound is propagating like that, and you are measuring at a distance R or and then 2R. So this point is say 2R, and this is R. So once you have measured at this point and once you have measured at this point, and the sound power levels or the sound intensity level, if you compare, so it's around 6 dB. That means every doubling of distance, the sound intensity level will become 6 dB reduction, okay. So that's the point which I wanted to make about that. So, and then these are, you have to be very clear that you must be in the far field zone, okay. So not in the near field zone. So we will talk about near field and far field. But when you are considerably farther away from the sources, so then these relationships hold good. And that's how you can, in fact, this is a way to even tell that whether you are in a far field or not. If by doubling the distance, your sound intensity level or sound power level is reducing by 6 dB, in fact the sound pressure level also will reduce by that same amount. So that will tell you that you are actually in the far field. If that relationship is not happening or not being observed, that means you are still not in the far field zone, okay, because that far field near field is a concept which is also dependent on the frequency at which you are talking about. So that's why this points needs to be considered while talking about far field and near field. Okay, so in the next segment we will talk about till now we never have discussed about anything related to frequency. We are continuously speaking about the amplitudes, that's how the energy content and all those things we are talking about. But what about if the piston oscillates at different frequencies, and then the sound which will be produced also will be at different frequencies. So then what, how to talk about them, the frequency bands and frequency components of sound. So those things we will be discussing in the next segment. See you in the next segment.